Mediation analysis allows us to assess the effect of one variable on another variable via a third variable, which we often call the latter a mediator variable or an intervening variable. This can be a great analysis tool when it comes to understanding what is presumed to be a causal relationship between three different variables, in which one variable is presumed or theoretically proposed to influence another, and then that one is proposed to influence still another one. So mediation analysis is used to investigate whether one, or more than one even, variable transmits the effects of a predictor variable on an outcome variable. Now, sometimes we refer to that variable that's in the middle, the one that's transmitting the effect, as being the mediator variable, and sometimes it's referred to as an intervening variable. Usually those terms can be used interchangeably, but I tend to find that people most commonly refer to the variable that transmits the effect as being the mediator. Now, it's important to note, too, there is this causal implication here because we are presuming that there is a causal flow from one variable to another variable to another variable. Now, this may or may not represent actual causality. Mediation can be a tool to test causal relationships, but inferring whether there is actually a causal relationship between two variables will depend a lot on the design, whether there were controls in place, and things like that. Still, if theory or the conceptual model you're working with indicates that there is potentially a mediational effect, or what we would call an indirect effect from one variable to another variable via a middle variable or an intervening variable, then mediation would be an appropriate analysis. So we can use both multiple regression or structural equation modeling frameworks when it comes to testing mediation models, or mediation analysis models as they're sometimes called. And specifically, we will be focusing on the path analysis approach, which is a specific form of structural equation modeling in this tutorial. And the reason for that is mainly because with modern software applications, it's easy to estimate the model in a single step, whereas a multiple regression approach would require that you do separate models. Sometimes, depending on what type of approach you're using to test the mediation, three or more models that you're going to be estimating. Whereas again, with a typical path analysis model, we can do that in a single step. Now, just like we would with a path analysis, commonly when we do specify or try to articulate or communicate what the mediation analysis model is that we're testing, we often use what is called a path diagram. So let's take a look at an example of a path diagram that can be used to illustrate mediation. So first, let's imagine that we have a predictor variable and an outcome variable. Let's imagine that the first variable is an employee's attitudes towards performing a behavior, and the outcome variable is the actual enactment of the behavior itself. Let's assume it's how often someone actually enacts that behavior. Now, as you can see here, we have a direct relationship or a direct relation, or in other words, what is called just a path here in our path model, and it's represented by the coefficient or the weight, the path coefficient weight called C. And so this would be the direct effect or the direct relation between attitudes and behavior, or in other words, the direct effect of a person's attitude on their behavior. And just like any other path diagram, we commonly model or depict the residual error. And so here you can see the residual error term here. This is common notation for it. So if we're talking about a mediation model, we might be asking this or trying to depict this. So yes, we're interested in the extent to which attitude does directly influence behavior, but maybe according to some theory we have or conceptual framework we're working with, we actually believe that attitude will affect behavior indirectly as well, and via this third variable here, which is intention. And so this, let's imagine intention is intention to perform this behavior. So here what we're saying with the mediation model is that a person's attitudes towards the behavior influences their intention to perform that behavior, and then ultimately their intention to perform that behavior influences their behavior. And as you'll see too, we also presume that to some extent, just having an attitude that's favorable about performing the behavior and acting that behavior is going to influence or increase the likelihood that someone actually performs that particular behavior or enacts that behavior. And the common notation we use is, you'll note that the direct relationship, the direct relation or path here, the coefficient that we're using here has now gone to C prime. So you see that C apostrophe here. And this is to indicate that now we're estimating the effect of this predictor variable on behavior, but in the presence of this mediator variable, because notice now we have what is essentially a multiple linear regression model here, in that we are looking at the partial effect of intention on behavior while controlling for attitude and vice versa. And so that's why we moved to C prime here, whereas before it was C without the apostrophe or standard C there. Now, importantly, the other conventional notation is that this first direct relation or first direct path commonly is labeled as A, and the second path from the mediator to the outcome variable is commonly labeled B. Okay, and so this is really the constituent parts of the mediation model right here. The ones that are most critical to the mediation model are your path between your predictor variable and your mediator variable, or path A, and your mediator variable and your outcome variable, or path B. So commonly, we will refer to the first variable or predictor variable as a predictor variable. You might see it referred to as your independent variable as well. Or the common notation, if you're doing this in more generic form, would be that this is your X variable here. Your outcome variable is commonly referred to as, well, your dependent variable in some instances, or just your outcome. And the generic notation would be this is your Y variable. And then your mediator variable is, as I mentioned before, either referred to as a mediator, a mediating variable, mediator variable, or an intervening variable. And commonly it's referred to, when in the generic form, as the M variable, because this is your mediator variable here. Now, we do have these underlying equations because this is a path analysis model we're talking about. And the same would apply if we were using multiple linear regression approach too. And so what you'll see here is generally we have three equations we're interested in. The first equation is the effect of that predictor variable on our mediator variable. And so here I've used the notation of A, so A being that first path on that direct relation from that attitude variable to the intention variable, or in other words, from our predictor variable to our outcome variable. And just as we would with any regression equation, we have our intercept, and we also have the error term here, the residual error in other words. Now the second equation would be the second part of the model, which is the effect of intention, which is our mediator variable, on behavior. And here we're using that common notation. This is the B pathway, so that coefficient is represented by B here. And then we also are looking at the effect of the predictor variable, which is the attitude variable here, and its effect on behavior. And we use the C prime coefficient notation here. And again, we'll have an intercept here. So this second equation here represents a multiple linear regression model because there's two predictor variables, whereas the first one's a simple linear regression model because there's just a single predictor variable. Now, finally, this third equation will be used in some instances depending on how you're estimating your mediation effect or your indirect effect, as we'll talk about in a little bit. And the third equation is not necessarily going to be one that you'll need, but according to certain approaches to estimating mediational effects, you might need this third equation. Now, the third equation is just that initial model I showed you that just looks at the effect of the predictor variable on the outcome variable. So attitude predicting behavior, that was the C pathway. And so you'll notice that this is not C prime, it doesn't have the apostrophe there. And again, this is a simple linear regression model, we'll have our intercept and a residual error term there as well. So as I mentioned before, the information that we're going to pull from these equations, we'll either use all three equations, or we might just use the first two equations depending on what approach we're using to actually test for that mediation effect, or what we'll refer to as an indirect effect as well. So let's also distinguish between two types of mediation. We have what's called complete mediation and partial mediation. Thus far, I've been showing you a partial mediation model. Well, a complete mediation model refers to a mediation in which the direct relation between the predictor variable and the outcome variable is 0, meaning that there's no estimated effect between your predictor variable and your outcome variable. And specifically, that is the direct effect. We're not estimating that as being anything other than a 0 coefficient there. And this is going to, what I'm referring to is in our path model, this would be that C prime pathway. Now, a partial mediation is, again, what we've been looking at thus far in those path diagrams. And this is a mediation in which the direct relation between the predictor variable and the outcome variable is non-zero. So we are estimating an effect, a non-zero effect between our predictor variable and our outcome variable in the presence of our mediator variable. And so in other words, we're estimating that C prime pathway. We're allowing it to be a free parameter, in other words. And so here's an example of how you might depict, using a path diagram, a complete mediation. So we're going to definitely have to estimate, always, the A pathway and the B pathway. But as you can see here, the dotted arrow line, the direct relation between the predictor variable and the outcome variable, the C prime pathway, this dotted arrow here indicates that it is a 0 coefficient. In other words, we're setting this parameter here, we're setting this coefficient, this path coefficient, to 0. Okay, so C prime is equal to 0. And when that happens, it means that we have what is referred to as a complete mediation. Now, in reality and in practice, these tend to be fairly uncommon. Usually, the predictor variable does exert some direct effect on the outcome variable, even in the presence or when controlling for the effect of the mediator variable. Still, sometimes according to theory, we might believe that there would not be a direct effect of the predictor variable and on the outcome variable when the mediator is present. And in that case, we would propose a complete mediation and test it accordingly. Now, partial, or another way to actually show the complete mediation is just not even to depict that C prime path. So here's perhaps a clearer way to depict it. And this is the same thing as saying that we're setting that C prime direct effect between the predictor variable and outcome variable to 0. Setting that C prime path to 0, it's the same thing. Now, partial mediation is what we've been looking at. And so here's where we expect there to be a non-zero coefficient between the attitude, or the predictor variable in this case, and the behavior variable, or what is the outcome variable in this case. We expect this to be non-zero, this C prime pathway. Again, this tends to be the way things work in reality, but not always, and sometimes there is good reason to believe that a complete or a full mediation is more appropriate. Okay, so now let's talk about the distinction between what I've been mentioning here and there, this idea of a direct effect and an indirect effect in the context of a mediation analysis model. So we're talking about a direct effect. These are just those directional relations, or those paths between two variables. In other words, if you're thinking of a path diagram, it's that directional, unidirectional arrow from one variable to the next. That is a direct effect. Now, an indirect effect is going to be specific to a mediation model because this is what we're actually testing. We're testing for the indirect relation between two variables via an intervening or mediator variable. Okay? And so this is that idea of that predictor variable influencing the outcome variable via that mediator variable. In other words, the indirect effect of the predictor variable on the outcome variable is being conducted or being transmitted by that mediator variable. So when we're trying to test for the presence of mediation, we're ultimately trying to estimate the effect, or the how much of an effect the indirect effect actually has, and whether it is significant. So again, here's the model we're looking at here. And so when we're thinking about an indirect effect, this is what we're talking about here. Or rather, a direct effect, this is what we're talking about here. These are the direct effects here. Your A pathway, your B pathway by itself, and your C prime pathway in this model. These are your direct effects here. Your indirect effect, in contrast, is going to be the effect jointly of A and B. A pathway and B pathway. And so we'll talk about different ways of estimating it. One is the product of coefficients, where we're actually multiplying the coefficients of these two pathways here to estimate the indirect effect. But what we're really saying here is that the predictor variable is influencing the outcome variable via the mediator variable here, or the intervening variable, as we can also call it. So how do we estimate the indirect effect? Well, there's different approaches for estimating an indirect effect. We can use a causal steps approach, we can use a difference in coefficients approach, or we can use a product of coefficients. Now, I'll start off by saying the causal steps approach, although it was one of the initial approaches, it gained a lot of popularity in terms of testing mediation, it required multiple steps, up to 4 steps, and it made some assumptions that weren't necessarily tenable and assumptions that didn't necessarily need to be met in order for there to be a mediation effect. And for that reason, we typically don't use the causal steps approach anymore. And part of the reason we've moved on from it is that now our statistical software programs and applications are much more powerful, and we can readily estimate these other 2 approaches with some degree of facility. So the difference in coefficients and the product of coefficients approaches under certain circumstances are actually going to be equivalent. However, we're going to focus on the product of coefficients approach in this lecture, as this is a very common approach. It's relatively easy to compute via modern statistical software programs, and it's a good way to estimate the indirect effect. So we're going to focus on what's called the product of coefficients approach, which I'll explain a little bit more about. So when we're trying to estimate that indirect effect using the product of coefficients approach, it's important to define what is this product of coefficients. Well, as I talked about earlier, it's this idea that we're actually looking at the product, or multiplying, in other words, the A and the B pathway coefficients. But that's not all we're doing, because in order to assess the statistical significance, we need to take that a step further. So in the product of coefficients approach, what we're doing is we're estimating the indirect effect by computing the product of the coefficients for those directional relations that comprise the mediation, which are those A and those B paths. Now, these respectively represent, again, that relation between the predictor variable and the mediator variable, your A path, and that direct relation between the mediator variable and the outcome variable, which is going to be your B path. So again, we're just talking about the product here. So that's what the indirect effect estimate is going to be. Now, in terms of determining the statistical significance of that indirect effect when using the product of coefficients approach, what we're actually doing is we're dividing that product of coefficients of A and B by its standard error, and the resulting ratio is then compared to a standard normal distribution or to some other distribution. And so just like we would, or similar to how we would with any other path coefficient or regression coefficient, in order to generate its p-value and determine its statistical significance. So another thing that I'll mention too is that within the product of coefficients methods, there's actually different ways that we can estimate the statistical significance. And so when we're talking about the product of coefficients methods, we can use classically what is called the delta method, or the multivariate delta method. And this is an approach for estimating the standard error of the product of coefficients and comparing that to the standard normal distribution to determine that p-value. Now, this is relatively easy to implement in modern software. The one downside is that when you have smaller sample sizes, so for instance, when your sample size is less than 50, it tends to show bias, this delta method. And so it's not going to necessarily give you accurate estimates of whether or not that indirect effect is truly significantly different from 0. Another thing is that the delta method has an assumption that the sampling distribution of the indirect effect is normal, which is not often the case. In fact, when we take the product of coefficients, the sampling distribution is going to tend to be non-normal or asymmetrical. So for that reason, often maybe we will calculate or compute the delta method approach because it's relatively easy to do, but typically we also, or just decide to do it instead of, we will use some type of resampling method in order to estimate the statistical significance of that indirect effect. And so resampling methods, a common implementation of resampling is the bootstrapping approach, which is where we take repeated samples from our sample with replacement. So we're just resampling from the same data. And so what this can allow is it's going to make it so that we don't have to assume a normal sampling distribution of that product of coefficients or that indirect effect that we're trying to estimate. And so for this reason, it can give us more accurate estimates of whether or not that indirect effect is actually significantly different from zero in real life or in the population, in other words. Now, just like the delta method, however, some of these resampling approaches will still tend to show bias in small samples, and there's been some simulation studies that have looked at this. And for this reason, some people are now recommending for small samples using a Bayesian approach in order to estimate the significance of the indirect effect. Now, in terms of different resampling methods that are available to us, commonly there's people use the percentile bootstrapping approach. There's also the bias-corrected bootstrapping approach, the bias-corrected and accelerated bootstrapping approach. And then there's also a variation. It's a type of resampling method that's similar to bootstrapping called the permutation method. And we also have what's called the Monte Carlo method. Generally speaking, if we have access to the raw data, we should be using the percentile bootstrapping approach. This is one of the best approaches to use, and this is what we'll actually focus on. Under many circumstances, the Monte Carlo approach will probably do about as well or come out at about the same. And then although we can estimate the bias-corrected bootstrapping effects or the bias-corrected and accelerated bootstrapping confidence intervals, rather, often we will now typically focus just on the percentile bootstrapping approach. But this is also something you want to look specifically at your sample, what it is you're estimating, and so forth. But all of these resampling approaches help us estimate a confidence interval of some type where we're looking to see whether our true indirect effect it's going to reside somewhere in that confidence interval, or we're confident that it's somewhere in that interval. And then the question is, does that interval include zero? And if that confidence interval does include zero, typically that's when we say, okay, this is not statistically significantly different from zero. If it does not include zero, then that's typically when we would say, okay, we have reason to believe that this indirect effect is statistically significantly different from zero. So this has been a brief introduction to mediation analysis. There's much more complicated mediation analyses that we can do and mediation models we can specify. We can have multiple mediations. We can have sequential mediations where you have a predictor variable, for example, leading to a first mediator, leading to a second mediator, leading to the outcome variable. And so there's different ways in which we can specify these models that get more complex. In this lecture, we focused just on one of the most simple approaches to mediation model, where we have one predictor variable, one outcome variable, and a single mediator model, or single mediator variable. And we also distinguish between that idea of a complete or a full mediation and a partial mediation as well. So this wraps up the lecture on mediation analysis.